Great. So now we have Joanna McDougall, right? And okay, thank you. So probing for passwords, floor is yours. Let me do this.
Good. All right, thank you very much. I hope you can hear me well. Is this a good place to stand?
Yes.
Okay, perfect. All right. So, yeah, thank you very much for being here. It's nice to have to hold a talk in front of an audience, actually. So, yeah, welcome to this presentation on privacy implications of SSIDs in probe requests. My name is Joanna McDougall, and I'm a PhD student at the University of Hamburg. And I'm really excited to present our research to you today. So let me tell you a bit about the background. In case a mobile device wants to connect to an access point or a router, there are two different means of connecting, of discovering each other. One of them is called active discovery, and the other one is the passive discovery. Passive discovery works by means of a router sending out beacons, and these beacons contain loads of information on the router, like capabilities, like the SSID, etc. And the other means is the active discovery, in which mobile devices send out probe requests, and these probe requests contain a lot of information as well. I've got a screenshot of a Wireshark capture here, and you can see three different bursts of probe requests here. Can you see my mouse? No, you probably can't, can you? Sorry?
That's bad. Thank you. Let's try to do like this.
Okay.
See? Do they change as well? Great.
Do I have a laser pointer somewhere, or so I can like on the screen? Or can you see my mouse on Zoom? Okay, and you can follow my mouse here too. So, all right. So we've got three distinct bursts. The first one is this one. You can see all the packets were sent within a very short time frame, and all of them were sent from the same MAC address. The interesting thing is that all of these packets in this whole capture were sent by the same device. So in this, the next burst, which was also sent within a very short time frame, you can see the MAC address changed. So that's called MAC address randomization. The third one, we can also see a different MAC address here. The next field that's interesting is the sequence number, and we can see that we've got an initial sequence number and then incrementally counting up the next sequence numbers. Same with the next burst. We start at a different number, at a randomized number, and then we count up. So these two means are kind of tracking protection mechanisms, making sure that in case other people capture probe requests, it's a lot more difficult to find out which device was actually the device we see, or whether that all corresponds to just one single device. But what we can also see in this particular capture is the SSID field here. We can see there's a set of SSIDs here, the same set of SSIDs is repeated here, and again here. So we can say this is a kind of fingerprint for this device. So it's obviously going to be easy to identify which device sent these sent these probe requests, despite the fact that we're using sequence number randomization and MAC address randomization. So again, Wi-Fi tracking via probe requests is used, for example, in trade fairs, in supermarkets, in pedestrian zones, just to estimate how many people are there and to estimate the traffic flow, etc. And there are tracking protection mechanisms in place, like MAC address randomization, sequence number randomization, and the omission of fields. And that's something I haven't said on the slide before. In newer devices, particularly Android devices newer than Android 9, or Android 9 and newer, a lot of fields are omitted. like for example, the SSID field. You try to send the SSID field as seldomly as possible, because otherwise people can be tracked even more easily. If you insert a network manually into your phone, devices older than Android 8 will assume that they're hidden networks, and then they will always transmit the SSID, which is kind of bad, and which is something that we will come back to later on in this presentation. So what exactly is this presentation going to be about? It's going to be about SSIDs in probe requests. We're the first to actually look at the content of the SSIDs, and we analyzed first of all what we saw there. That's called the PNL, the preferred network list. That's the list of all known networks for a specific device. And then we're looking at localization of the networks, because there are maps available on the internet, for example, wiggle.net. And you can just go to wiggle.net and insert your SSID there and just see where it exactly is in the world. It's pretty exciting because it makes sure that, well, you know where your network is, but pretty much everybody else could know where your network is too. And if your device is transmitting your SSID, people can know where your home is, for example, where the cafe is that you've recently used, where your work is, etc. As an example of a query on Wiggle that I recently made for all networks in Hamburg called EduRoam, and you can see all the university locations here. You can also make API queries on Wiggle, which is something that we did, and I'll show you in a second. So that's where we get into the really interesting part, the field experiment that we did. So we talked to the Ethics Commission of the University of Hamburg to make sure that all of this is happening in ways that preserves the privacy of people in the pedestrian zone. We sat down for three times 1 hour in the city center of Lübeck, and we took 6 receivers and listened for probe requests on, with 3 of them on the 2.4 gigahertz band and 3 of them on the 5 gigahertz band. In total, we captured 252,242 probe requests and found that 23.3% of them contained an SSID. And these SSIDs contained some very interesting things. So a manual inspection revealed that quite a lot of them contained 16 to 20 digit numeric strings, such as they are very typically used in Germany for as initial passwords for home routers, for Fritzbox and telecom home routers. And some of them were even prepended by PW: or WPA: and it was kind of mad to see these things, because you thought, how did they get in here? And our assumption is that people inserted them manually into the when they tried to manually insert them into their preferred network list, but because they probably have older devices, they're considered hidden networks by the device. And then the device says, okay, I'm looking for this hidden network with this 16 to 20 digit numeric string as an SSID. Yeah, 11.8% of the bursts we recorded contained potential passwords. And that's quite something, I think. That's quite something that people wouldn't want, I'm sure of it. With respect to other strings we found, in loads of bursts, we saw that there were various networks with one name, but then spelling variations of these networks. And for each spelling variation, you can imagine, there's not only this one spelling variation, but loads and loads and loads of different variations that people tried out. And that means that the fingerprint that this particular device has is increased manifold. And again, tracking is made so much more easy on these for these devices. In order to automatically evaluate how many devices actually transmitted these potential typos, we calculated the normalized edit distance. So the edit distance between 2 strings is you add 1 per each substitution, deletion, or addition of character. And then because you've got this number that really doesn't represent anything with respect to the string length, we normalized it by dividing it through the longer string length. We set the threshold to 0.3, which means that at least 30% of the string had to be, or at most 30% of the string was allowed to be different in order for the two strings to be considered similar. Yeah. And of course, we calculated these things only over the strings contained within one burst. So we knew that all of these were from just one device and not from several devices. We also did a manual analysis on all of the strings that we found, because of course there could be different router names corresponding to different router models, which would actually be different networks. But we found out that none of such legitimately entered SSIDs were contained in our potential typo list. In total, we found that 19.9% of the bursts contained such potential typos. So 19.9% of the bursts were a lot more fingerprintable than the others. In addition to these findings, we also found a store password, 106 distinct first or last names, sometimes even in combination, 3 email addresses, 92 holiday homes, and 1 hospital, also in various spelling variations. And all of these things I would consider, most of these things I would consider some privacy value infringements, because things like, for example, a recent hospital stay, a recent holiday home, or especially first and last names, are things that I wouldn't want to transmit freely. Most people probably wouldn't just give them to you or tell them to you if you just walk up to them in a busy pedestrian zone and say, hey, when have you last been at the hospital? Just tell me. So in addition to these evaluations, we also thought it would be very interesting to find out whether we could geographically localize all of the SSIDs via the Wiggle map, and inserted all of them into the API. We found in total we had 104,078 unique SSIDs, and this is kind of a nice takeaway. 38 of them were not resolvable, which is because Wiggle doesn't map special characters, and these 38 contain special characters. So if you want to hide your network from Wiggle, insert some special character. Yeah, so the 1,440 SSIDs we were able to evaluate contained 334 unique locations, 377 cases of multiple locations, and we were unable to localize 50% of them, or approximately 50% of them. We did the same for the we did the same for the password evaluation, and found that only a single one of them evaluated to a location, and that, in our opinion, makes it very. We think that it's very, very. It's a sure sign that these passwords, or these strings we evaluated as passwords and considered to be passwords, are really passwords and don't correspond to any actual SSIDs and any actual networks. For the typo evaluation, we did the same. We inserted them in the Wiggle as well, and found that 41.9% of them were resolvable, which also kind of makes sense, because the larger the amount of crap that is that we insert into the SSID field, the less of them we will actually be able to resolve. The limitations of this evaluations are, of course, that Wiggle shouldn't actually map hidden networks, and the only networks that a mobile device should query for with an SSID in their probe requests are hidden networks. But it could be that multiple networks with the same name exist, or the hidden status was just changed recently, or that the network was manually added in Wiggle, which we consider rather, that probably doesn't happen too often. Or, and that is the most likely explanation, that very old mobile devices were in use. As I said, devices older than Android 8 and Android 8 assume that every single SSID you enter manually is a hidden network. So they will always query for these networks using the SSID. So this is all very nice, but how do we protect ourselves from it? Well, first of all, it would be nice not to broadcast any SSIDs whatsoever. But seeing that there are hidden networks and that we still need to protect ourselves somehow when connecting to a hidden network, we would like to propose a scheme in order to protect our SSIDs from being recorded by other people. We could, of course, just hash them, just insert them into some hashing algorithm and then transmit them out like that, but that would still leave us trackable. So we thought we'd add some randomness. And in our case, we thought, okay, the MAC address and the sequence number are transmitted with every burst as well and are changed after every burst. And that gives us a lot of randomness. It gives us at least 36 bits of entropy. 48-bit for the MAC address. The MAC address contains two different identifiers. The first 24-bit are kind of a company identifier, and the last 24 are actually randomized. So we suggest that, or suppose that about 24 bits of the MAC address are randomized enough for us, for our purpose, and then another 12-bit from the sequence number, resulting in 30 bits, 36-bit altogether. To compute the feasibility of all this, we computed the computational overhead and prototyped everything on a Raspberry Pi and found that on the Raspberry Pi, a comparison of a string in comparison to a comparison and hashing again and stuff, results in an overhead of 153.7% increased time, which is quite a lot. And then we thought, well, a Raspberry Pi usually doesn't have any cryptographic hardware acceleration. A router most likely does, though. So we prototyped the same on an Intel i5 processor and found that the overhead was only 53%. And we consider this much closer to what is probably the real overhead in such scenario. In addition, the real life evidence we recorded was that we only saw 5.3 probe requests per second that actually included an SSID. So on only 5.3%, 5.3 probe requests per second, an overhead of 53% is absolutely legitimate as well, particularly with respect to the privacy gains we have using this scheme. In addition, we computed the bandwidth overhead and found that it amounts to an overhead of 14%. And we also think that these 14% are legitimate with respect to the low amount of probe requests we recorded in a busy pedestrian zone. In addition to modifying or to these modifications on the network level, we proposed some UI modifications. I'm going to skip most of them now because yeah, it's rather tedious to listen to them in this presentation, but I would yeah, I would suggest to read the paper in case you're interested in them. And I will just go into detail a bit on this third modification that we propose, and that's to introduce a reduced visibility mode where only passive discovery is used. That amounts to three different things. First of all, a higher battery usage. Second of all, slower connection with the network because passive discovery is just slightly slower. And third of all, we would have, well, now it would be nice to have my notes here. The third is that it would be impossible to connect to a hidden network. And that's, of course, something that we would take into account in case we know we never connect to hidden networks. But at the same time, if we do connect to hidden networks, we couldn't use this reduced visibility mode. But it would be something that I would, for example, absolutely turn on if I went into a busy pedestrian zone where I know they're using Wi-Fi tracking, or if I went to a trade fair or maybe a shopping center or something like that, where I just want to increase my invisibility. Yeah. So we've seen that a lot of SSIDs that we recorded contain personal information. So we would like to motion for SSIDs being considered personal data. The recording of probe requests is already kind of a gray field because MAC addresses are typically considered personal data. But then again, if we've got most devices using MAC address randomization, how can we say that a MAC address is actually a personal item if MAC address randomization is in use? So a lot of vendors of Wi-Fi tracking devices are saying no, because of MAC address randomization, Wi-Fi tracking is not tracking on personal data anymore. But we say, since so much personal data is contained in the SSID field, it should be considered personal data. And then, of course, the favorite topic for all people in security, longer OS support lifespans. It would be absolutely brilliant if devices were supported for a longer time than only 2 years, which, of course, I can only say with respect to most Android devices or most Android manufacturers. And yeah, using old devices is great for sustainability. Using old devices is also terrible for security, because as we saw, the older the device, the less likely it is to introduce new techniques such as MAC address randomization, such as sequence number randomization, such as omission of the SSID field, and such as not considering manually added networks as hidden networks automatically. We've got some future work too, which we're working on right now. First of all, we want to implement the hashed SSID scheme. Second of all, and this is something that I really hope somebody could get into a discussion with me about, because I haven't been able to find out too much about this, is to, instead of using the randomized MAC address, to implement a generic address, like for example, just 00000, as the sender address, and then evaluate that for multiple devices, because that would make bursts indistinguishable. And the OUIs, the organizational unit identifiers, wouldn't be contained in the MAC address either. And it would be so interesting to find out what would happen if so many devices just probe with the same MAC address. And then, in addition to all of this, we would like to evaluate the accuracy of the table 1, which I took out of my presentation, but it's still in the paper. The table is accurate with respect to the specification of both Android and iOS, but we found some divergence with respect to the actual things we saw in the field. Like, for example, Samsung and Apple devices sometimes didn't actually do what the specification said. So we would like to investigate a bit further there. Yeah, and with this, I would like to thank you very much for your attention and for coming here. And I hope we'll all have a wonderful rest of the conference. And I'm very happy to answer questions now and to get into lots of discussions with every one of you. Thank you very much.
Thank you. So, any question from the audience?
Yep.
If you want this mic.
So in one of your last slides, you said that you would consider a MAC address which is all zeros and how it would work. But I don't know if that would work, because in Wi-Fi, like, every client broadcasts to everyone, right? So the MAC address is a way for a client to know which packet is for them. So then if a router would answer, then every client would think the packet is, you know, for them, or no, it's destined for them. So I would think intuitively that would break some things. And secondly, I think that would also reduce the security of your hash scheme. So if you would, because you're using the MAC address as entropy, right? So
yeah, of course, yeah.
If it's all zero, then it has zero entropy. You only have 12 bits of entropy. That's not a lot. So you might want to add an additional identifier in the protocol. So with that said, I was wondering, because you proposed this hash SSID scheme, I was wondering if you have actually proposed this as an RFC of some sort, or to the responsible bodies for standardization.
No, we haven't yet. We're working on implementing it right now, and then we just wanted to evaluate it for various devices to find out whether it works. If you've got a lot of devices transmitting the same thing and listening on the same MAC address. With respect to your second question, yeah, absolutely. If we use the MAC address as input for our hashed SSID schemes and suddenly only use zeros, that would absolutely break it. You're right. That would leave us with 12 bits of entropy instead of 36, and that would be disastrous. So we would have to look for another source of randomization. And with respect to your first question, let me think, what was your first question?
About the MAC address, how it would interact with the router.
That's right. We think that it might actually result in a lower amount of probe requests being transmitted, or a lower amount of probe responses, which are kind of like the beacons that routers send, because in passive discovery, you kind of have to say, hey, I would like to know which networks are available right now, and then you have to keep the radio on for a longer period of time in order to capture all the beacons sent by the routers, because they're only sent every 102.4 milliseconds. In active discovery, you send out the probe request, and then you just have to turn on the radio for a much shorter amount of time, which is also why it's more energy efficient, because you only have to listen on that in that particular second. And then in that particular second, if somebody answers and sends you their SSIDs and everything, and sends you their probe responses, you will receive the answers you were looking for. And if multiple devices asked for or sent out probe requests at the same time looking for the wildcard SSID, which means that all routers in the area would just respond with their SSIDs and their probe responses, maybe we would even reduce the amount of probe responses that would have to be sent.
So you would rely on the fact that the device would only turn on its antenna to receive for a very short time.
Exactly, that's exactly what's done in active probing. Yeah.
Okay, yeah, that makes sense. One final question: in the hashing scheme itself, you consider SHA-256, which is a very standard choice. Would you consider different types of hashes, because there's different types which might work better on low power devices? I know you said that a router might have crypto hardware, which is the case, but it might depend on the model. So it might also be interesting to consider specific hash algorithms that are designed for low power devices.
Yeah, absolutely. That's a good idea to look into other schemes too. We just thought we'll take the first scheme that has 256 bits of length, because the SSID field has a length of 256 bits. So that was like, yeah, okay, it matches, fine. And we don't have to transmit a salt in addition. If we used a shorter hashing scheme, we could also transmit a salt in addition, and then we wouldn't have to rely on MAC addresses and sequence numbers to be properly randomized.
Thank you.
Thank you.
Thank you for the presentation. I have a question about sorry. Whether have you tried multi-access point, where multi-access point in an environment broadcast the same SSID, whether there is any specific feature in that environment compared to single access point with single SSID?
So if I understand your question correctly, you're asking whether we've tried out an environment where we've got multiple access points, all of them transmitting the same SSID.
Because like in a specific setup, yeah, exactly, a multi-access point with the same SSID.
I'm not completely sure how that would improve anything or how that would change anything. But if we've got multiple access points broadcasting the same SSID, a mobile device will usually connect to the one with the best signal that's closest. That's also how, that would usually be the case. And while a mobile device is connected to an access point, it will only query for other access points with the exact same name, and it will then connect to the access point with the better reception once it receives that. Okay. Did that answer your question?
Yes.
Okay, perfect. There was another question here.
Well, thank you for your interesting research. I would like you to show the slide number 19. Yeah, here about the operating system support. Maybe it's not a question, it is a suggestion. Nobody wants to maintain old versions of the operating system. And there is a problem with Android devices because they usually offer only 2 years of maintenance. And I think maybe one of the solutions would be to force Google and other Android device makers to offer upgrades to the operating system. Perhaps that would be much better. And yeah, and this is not the only problem. I see that there is another problem regarding hardware, because in Apple chips, they usually find some vulnerabilities. I think that on Android devices, there are also some vulnerable chips. So this is the second, maybe the second suggestion how we can. So the second suggestion would be to change such devices and such vulnerable CPUs. So this is just a like comment.
Yeah, and with respect to the first you said, it's really a shame that Android vendors typically only support their devices for 2 years. That's of course a question of money, right? Because the people don't want to sell the devices older than 2 years anymore, so they want to make people buy more devices, new devices, and this is terrible with respect to sustainability. Terrible with respect to security as well, because obviously when you buy a 1.5-year-old mobile device, because it's a bit cheaper than the half-a-year-old device, you will only have half a year of support. And after that, you won't have a recent device anymore. You won't have recent security patches anymore, and that's absolute crap. That's something that shouldn't be the case. And somehow the vendors should be pressured into supporting them for a longer time. But yeah, you said some CPUs then contain security flaws at some point. That's absolutely the case. And I'll have to grant Apple this here. It's really nice how long they support their devices. I think they recently upgraded the 6th Apple iPhone for the last time. And I think that's from 2014 or something like that, maybe even older. And that's a really nice and long support lifespan, particularly with respect to how fast the strength of the devices changed and increased, and with how, just in general with how long this device is supported. Yeah, I agree. Yeah.
I just agree on this. So since you are thinking to, in some way, reinvent the way how your device interacts with this SSID, no? Maybe we can also try to, let's say, do a step further, no? Maybe you should say, okay, it's a hidden network, so I know when it's time to turn it on and start asking for that specific SSID.
Yeah.
This is maybe the first. So one of the additional proposals that you can try to include. And also another modification could be, okay, instead of me following all the possible SSID that I know, it should be something like, hey, all the SSID that are here, could try simply send me their details so that I can see I know any of them. So the idea is that all the devices should only do exactly the same thing.
Yeah.
I don't know, maybe it could be some other proposals that you can in some way see. So since it's time to rethink, because now privacy awareness is much higher than before. So maybe it could be also an option to rethink most of the steps.
Yeah, that would be very nice. And the first thing you suggested is actually very close to the introduction of a user prompt that we made here that I didn't really go into detail. But that's to prompt the user after inserting a network into their mobile device and after connecting to it for the very first time, for specific things, like, for example, how long do you want to store this SSID? For me particularly, I would say the conference Wi-Fi, I need for 5 days, maybe, probably less. Yeah, 3 days would be enough. And after that, it can be deleted from my phone. And the next time I'm here, I'm going to insert it again. And the probability that it will have changed during that time is rather high. And the probability that I will query for it in the meantime, while I'm not at the conference, is 0. So it would be nice not to have that in my PNL at that time. And in addition, we've got adjustable auto joins for on pretty much all recent devices now, on Android and on iOS. But it's kind of difficult to find these auto join functions. So that would be one of the things that we would want to include in the in such a user prompt as well, where you would just be prompted, do you want to always connect to this network? And I would say, if it's a cafe network, no, I don't. I don't, because I only walk past here every once in a while, and during that time I don't want to connect to it because I know it's kind of prone to Wi-Fi tracking. But whenever I sit down in the cafe, I do want to connect to it.
So it could be also joined to the this geolocalization. So you can in some way mesh also this kind of information.
Yeah, that would be good. Yeah.
It's a time for a good proposal. Inventing SSID mega.
Yeah, that would be nice. That would be really nice. Yeah.
Thank you.
Yeah. Thank you. Are there any other questions?
Thank you again.
Thank you.